Let's continue with the fourth and last part of this talk, bifurcating minimal surfaces with symmetries. So this is the fourth part, minimal tori in three-dimensional ellipsoids. So using the same notation in the last part, we'll consider the ellipsoid with semi-axis A, B, B. So here we're adding a few extra symmetries to the situation. We have both of these and both of these equal to one another. And I want to again emphasize the isometries coming from the ones in orange. So if I look at the isometry group, it contains an O2 coming from rotations and reflections about the origin in that X3, X4 plane. And there's another O2 from the X1, X2. So I'll focus on this orange O2 acting on these two coordinates. All right, so there's a trivial branch of minimal tori, which are given like this, when this is equal to 1/2 and this is again equal to 1/2. Okay, and for all values of A and B, these are minimal tori. So in particular, if A and B are equal to one another, these are the Clifford tori, the Clifford torus, I guess. Okay, so the result about this that we have, and this is in again joint work with Paolo Piccione to appear very shortly, is that if A is a positive number less than B over the square root of 3 for these values of A, then there is at least one torus, which is G-invariant minimal torus embedded in this ellipsoid, other than that one. Okay, and there's at least one other solution. Okay, so a few points about minimal tori in spheres. Of course, a very celebrated result was the proof of the Lawson conjecture by Simon Brendel, that on the round sphere, there's only the Clifford torus, right? Every embedded minimal torus is congruent to the Clifford torus, so that's the only solution. So on these ellipsoids, as A becomes much smaller than B, then other tori appear, bifurcating from a family that contains this torus. So a result of White about 30 years ago is that every metric with positive Ricci curvature on the 3-sphere has at least one embedded minimal torus. And in the same paper, Brian White conjectures that there should be at least 5 embedded minimal tori. Now, of course, the metrics we're working with have a lot of symmetry, so there's infinitely many trivially. There's, as soon as you have one, you have infinitely many, because you have orbits of these minimal surfaces. But but it'd be interesting to know if we get 5 different ones up to congruences, right? So 5 geometrically different ones, right? I guess what we're saying here is that there's at least 2 up to congruence. Okay. Even though there's infinitely many trivially. All right, so the symmetry reduction setting is very similar to the last part, part 3, in which now I just flipped a bit the semi-axis. So the first 2 are equal and the last 2 are equal. So if you trace back what we did, the same thing goes through here. We have that the orbit space is a 2-dimensional ellipsoid, a hemisphere of a 2-dimensional ellipsoid that looks exactly like that. It has boundary there. So this, you can think of this height function here. Nope. Let me cheat and use this. There you go. So as being R. And here we have, of course, the other 2 axes, X1, X2. So the boundary is the set where R is equal to 0. These are the fixed points of the action. And the volume function, again, is 2 pi R. So here R, if you solve for R in this equation, you see that it's that. So again, it's 0 on the boundary. And again, we look at this degenerate metric. This is just like the one we had before for spheres. For spheres, we were looking at these geodesics, these free boundary geodesics, So even though I was drawing like a picture like flattened down, this all of these are trivially these are equators, okay? And they are spheres. So in this case, we're looking for tori. So we don't want things that go to the boundary. We want things that stay inside. So for example, geodesics, geodesics like this, okay? So we want closed geodesics. So let me put here, we want closed geodesics. And let me also mention that here we have isometries as well, right? So these rotations are isometries. So we have a rotationally symmetric metric, and these Killing fields give a first integral to the system of ODEs. Okay, so there's a first integral. And this is similar to the other applications of this reduction principle in the literature. The ones we discussed in the third part of the talk do not have this first integral. So they're this is exactly that vertical branch. So this is the very degenerate case where there's a even larger isometry group, 2 copies of O2. Okay, so we want to find closed geodesics, bifurcating from a trivial one. The trivial one is, again, flattening the picture to look at it, looks like this. That's the Clifford tori, let's call it. So if we put polar coordinates on this domain, which is the orbit space with the conformal metric, we can then look at these radial segments starting at the origin, going to the boundary. So let's say if this angle is theta, this here is sigma theta. And then I can write down geodesics starting from all the points here in sigma 0. So for example, one of them will surely close up, and that's the one coming from the torus, the minimal torus. And let me parameterize here the segment sigma 0 so that this is exactly 0, okay? So parameterize it in such a way that just to have the trivial solution over the 0, so rho s comma 0, let's say is this starting point, rho s parameterizes sigma 0, let's say in this way, right? So the map that sends s to rho s comma 0 in sigma 0 is so that gamma 0 is the trivial closed geodesic. And the starting vector, the starting velocity here will always be dd theta. Okay, so we always shoot the geodesic up with vector dd theta. Okay, so these ones perhaps, go on and maybe do something funny. Some of them might, well, let's see, some of them might go up and come down again and close up, right? So that's the kind of thing we're looking for. So namely, if I have one of these geodesics that goes up and then maybe it goes up and like has to actually have to intersect, so do something like this. But maybe when it hits this guy, sigma pi, maybe it does so orthogonally. If that's the case, well, it started orthogonal there, hits orthogonal on the other side. I play the same game, I reflect. So these reflections about this diameter are again isometries. And then I would have a closed geodesic, right? So if I find geodesics that meet this guy orthogonally, that meet sigma pi orthogonally, then I can reflect and lift back, and I will find closed geodesics, hence downstairs, hence tori upstairs, minimal tori upstairs. All right, so to find them, let's remember the metric is rotationally symmetric, right? So the conformal metric, so I can write it in this way. Okay, it doesn't matter for the purposes here what this function is, even though it can say a lot about it. Let's imagine we write the geodesic in coordinates as well. Then it's a very classic exercise in Riemann geometry. When you teach undergraduates on it, that the geodesic equation is the system here. So the second order ODEs in the coordinates. And because you have the Killing field dd theta, there's a conserved quantity coming from that length, right? So it's actually theta dot times the square of phi, so phi rho squared. So this guy here is constant along any geodesic, okay? From that, if this constant is 0 or non-zero, since the function is always positive, you see that theta along the geodesic, it's either a constant or monotonic. Okay. If it's constant, then we have one of these radial geodesics, right? That's exactly, again, half of a sphere, half of a minimal sphere, as we discussed in the previous part. If it's not constant, it's not one of these segments, then it's monotonic. That means it keeps going, right? So it keeps rotating, so eventually you'll hit sigma pi. So I can define this function, again, set up so that zeros will be solutions. This function captures the angle at which, when I hit here, let me try to draw this again. When I hit there, I look at this angle of this vector, this tangent vector, and see if it's pointing exactly down or not, right? So I see the angle it makes with sigma pi to see if it hits orthogonally. And if it does, well, then we're in business. Then we're, for example, like this, because then I can reflect and lift, as we discussed a moment ago. So 0 is a solution for all values of A, because this red geodesic will hit orthogonally here for all values of A. Again, you don't really see A in this picture. Remember, A, well, I'm squishing this thing down, right? The parameter has to do with this height, and I'm squishing the whole thing down. So, but anyways, so we can look at the linearized problem as we did before. And the linearized problem here, again, will have something to do with endpoints of endpoint values of Jacobi fields. So let's say JA theta is the Jacobi field along the geodesic gamma S. Gamma S is the geodesic leaving from row S. So this is, let me maybe label that here. So this is gamma S, this is row S, and the red geodesic always leaves from row 0. So, oops, too much. I guess I have gamma 0 there, but anyways, so this is row 0. Okay, so again, remember theta is monotonic, so I can parameterize it in terms of theta. And the Jacobi equation is the linearization of the system, the ODE system I had upstairs, and it looks like this. So the derivative df/ds will be precisely given by the endpoint value. So this is R a dot when theta reaches pi. And the mixed derivative, again, is dda of this endpoint value. Okay. And this is a very simple ODE, right? This we can actually solve by hand with the given boundary conditions. So solutions are sines and cosines. We're interested in cosines. It's like the even version of the previous problem. So solutions here are exactly cosines of, well, I take a square root of that number. So 2a divided by square root of a squared plus b squared times theta. Okay. And this is a solution that satisfies the boundary conditions whenever this number is an integer, right? Whenever, you know, these are the eigenvalues that you get on a circle, these are squares of integer numbers, right? So Ra dot pi is equal to 0 if and only if this number 2a over square root of a squared plus b squared is an integer, right? Let's say equal to m. Now, a divided by square root of a squared plus b squared, this is always less or equal than 1, right? It's actually less than 1 because both a and b are positive numbers. So the only way this is an integer is if this fraction is equal to 1/2, and then 2 times it is equal to 1, since a and b are positive. So that's the same thing as saying that 2a divided by square root of a squared plus b squared is equal to 1. And then you can solve this, and you see that this is only when a is equal to b divided by square root of 3. So this is the only degeneracy instant along this family. So at that instance, we can compute the derivative, dda of Ra dot. And you will see that this, when a is equal to b over square root of 3, this number turns out to be positive. Okay, so the important thing, again, by Krandl-Rabinovich is that this number be not 0. So we have this is 0, this is not 0, we get bifurcation. So by Crandall-Rabinowitz, that's 0. This is not 0. So this is a bifurcation instant. We have a local branch going through there. Okay. Now, remember, this local branch will be something that can be extended. It's actually non-compact by Rabinowitz's global bifurcation theorem, because it's the only bifurcation branch. That's the only degeneracy instant. So it can't reattach, because if you were to reattach, there would be another bifurcation instant, and there's not, right? So it must go on forever. It must be non-compact. So it could go, for example, to infinity. But by, so let me write that down first. So non-compact. But by the Lawson conjecture, right? By the proof of Lawson conjecture, A equal to B is a barrier, right? You can't have two tori there. There's only the Clifford torus. So this curve cannot cross there. It could go close to it, but maybe it does. But if it goes to, if it's non-compact, the only way it can be non-compact is that it must do something like this. It must go all the way to this point. Okay. Again, it cannot go straight up because of properness. So the branch persists for all values less than b over square root of 3, as it cannot cross A equal to b, as I mentioned by Brandel's proof of the Lawson conjecture. Okay, so this completes the proof of this theorem that there's at least two solutions. There's the trivial one and the one that bifurcates. Okay, and that concludes the fourth and last part of the talk.